The bunch of formulas we have just derived is rather complicated. So let us try to understand them a bit better by actually using them in a calculation. The problem that we are dealing with here is that of a perturbed two-dimensional harmonic oscillator, where H0, the unperturbed Hamiltonian, is simply that of a symmetric 2D harmonic oscillator, px square by twice m plus py square by twice m plus half m omega square into x square plus y square. On top of this, we have added a perturbation v, which is given by k times xy. Now the Hamiltonian, the full Hamiltonian, H0 plus v, happens to be exactly solvable, and we are going to illustrate this exact solution first. Now the exact solution can be figured out just by writing out the total potential energy. This v is not the perturbation that we wrote down a while ago. This v is the total potential energy of the system, which of course is the sum of m omega square x square plus m omega square y square plus 2k xy into 1 by 2. So this is half x transpose Vx, where this x with a bar underneath is really the column vector written with x and y as elements, and this V bar is a matrix which expresses the quadratic form sitting here. And as we know from the theory of small oscillations, the frequency of normal oscillations for this particular system, omega plus and omega minus, the two frequencies, essentially will be determined in the following fashion. M times omega plus minus whole square will be the eigenvalues of this particular matrix V bar, where V bar is simply the matrix formed by taking the coefficients of this quadratic form, m omega square here, m omega square here, and the off-diagonal term is being split up into two terms, kxy plus kyx, and that's why you have two k's in the off-diagonal positions. Now the eigenvalues of this particular matrix is very simple to figure out. M omega plus minus square, the eigenvalues, will simply be given by m omega square plus minus k. That's a very straightforward calculation. So omega plus minus, the normal mode frequencies, are actually related to the unperturbed frequencies omega by this relation. There are two normal mode frequencies, one is higher than omega, the other is lower than omega, and omega plus minus is simply omega times square root of 1 plus minus k by m omega square. So classically, this system essentially is composed of two independent oscillators corresponding to the two normal coordinates, and quantum mechanically, it's of course two independent harmonic oscillators again corresponding to the two normal coordinates. And the energy for the oscillators now is given by two quantum numbers, one for each oscillator, and I've decided to call these quantum numbers n plus and n minus. So the energy corresponding to the state with n plus and n minus is simply h cross omega plus times n plus half plus h cross omega minus times n minus plus half. This is just the standard result for harmonic oscillators that you all know. It's just that you have two uncoupled harmonic oscillators and the total energy is the sum of the two individual harmonic oscillator energies. N plus and n minus, of course, are quantum numbers which can take values 0, 1, 2 and so on. Given what I have said right now, you would of course realize that there is no reason for trying to solve this problem by using perturbation theory. After all, the exact results are already known to you. However, we have already done this once before. We have solved a problem using perturbation theory where we knew the exact result perfectly well, and that was primarily because we wanted some practice before we could use the same method for more complicated problems. And that is exactly what we want to do here. Now let us take a look at the perturbation method for solving the same problem, and we are going to start by taking a look at the unperturbed problem. Now the unperturbed problem is simply one in which you have two harmonic oscillators, two identical harmonic oscillators both with the same frequency omega, one along the x, the other along the y, and just by using the standard raising and lowering operator formalism, we can simply rewrite the Hamiltonian as a sum of two Hamiltonians. In fact, this H0 expression that I've written here is simply a sum of h cross omega a dagger a plus half, that's for the x oscillator, and h cross omega b dagger b plus half, that's for the y oscillator. Of course, this expression that we have written down here is simply the sum of these two. And here A and B are basically lowering operators. I have not written down A dagger and B dagger because they are simply adjoints of these. And the only difference between A and B is simply the fact that instead of x and px, which is sitting in A, B has y and py. So basically the same theory goes through completely. And our familiar ideas about harmonic oscillator energy eigenstates or number eigenstates, which translates to energy eigenstates, simply leads us to this expression for the unperturbed energy eigenstates. The unperturbed energy eigenstates can be labeled by two quantum numbers nx and ny. And nx and y, the ket, is simply what you get when you apply A dagger, the raising operator for the x oscillator, nx times, and B dagger, the raising operator for the y oscillator, ny times, on the ground state ket 0. And this root over nx factorial ny factorial should be a familiar normalization factor. Now, while this gives you a complete characterization of the energy eigenfunctions, the energy eigenvalues, you can easily see, are given by epsilon nx ny. Remember, we have been using epsilon for the unperturbed energy eigenvalues. So epsilon is labeled by two quantum numbers nx and ny and is given by h cross omega into nx plus ny plus 1. The 1 here, of course, is because you have one h cross omega by 2 for the x oscillator, another h cross omega by 2 from the y oscillator. These are, of course, the vacuum level energies. And these states nx and y are mutually orthonormal. So nx and y bra overlap with nx prime and y prime ket is simply delta nx nx prime, delta ny ny prime. While this does give me a complete characterization of the energy eigenvalues and eigenvectors of the system, note that this expression for energy or the unperturbed energy levels immediately tells us that the energy does not depend on nx and ny individually but on their sum. So basically you can characterize the energy levels with a single quantum number n, which is the sum of nx and ny. So instead of labeling energies by nx and ny, I can label them with this n, which is h cross omega n plus 1. And n being the sum of nx and ny, where nx and ny can only take values 0, 1, 2 and so on, it's easy to see that n can only take values 0, 1, 2 and so on. Of course, this labeling makes it clear that these energy levels are actually degenerate, because for a given value of n, you have a fixed value of the energy, but there are multiple states which correspond to the same value of n. In fact, there are exactly n plus 1 energy eigenstates which corresponds to the same energy epsilon n. So the degree of degeneracy for this level, d, is n plus 1. And these states, borrowing the notation that we used a while ago, the unperturbed energy eigenstates phi n are labeled by an additional label I, and here for I am just using the nx value. So since the total of nx and ny is going to be n, if nx is I, ny of course has to be n minus I, and I can run all the way from 0, 1, 2 all the way up to n. So that gives you n plus 1 states in all, each and every one corresponding to the same energy epsilon n. So here we have a degenerate system, except for the ground state energy where for n equals 0, which of course can only occur for I equal to 0, and that means it's not degenerate at all. All other energy levels are degenerate. Then first excited energy level, the one corresponding to n equals 1, is 2 folds degenerate. The next energy level is 3 folds degenerate, and so on. So determination of the energy corrections to the levels because of the perturbation kxy, will involve degenerate perturbation theory in general. The only exception, of course, is a ground state, which is non-degenerate here. Now, this is a particularly simple system which exhibits degeneracy, and because degenerate perturbation theory is a bit more complicated than its cousin, the non-degenerate perturbation theory that we have studied earlier, I decided that we will take this very simple example to sort of explore the details of the calculation. Now, as we have already seen, to figure out the first order energy corrections in degenerate perturbation theory, as well as figure out exactly what the unperturbed energy level really is, what we need to do is make use of the secular equation. The secular equation is nothing other than the eigenvalue equation for the matrix which you create by taking the matrix elements of the perturbing potential V between the degenerate energy eigenstates. So, if you take the overlap between the phi ni and phi nj, where phi ni and phi nj are of course the unperturbed energy level eigenfunctions that we had just talked about, we get the elements that will build up the matrix whose eigenvalue equation we need to solve. And in order to figure this out, that is, figure out the matrix elements of k times xy, it's definitely a good idea to rewrite x and y in terms of the raising and lowering operators. And using the fact that x is square root of h cross by twice m omega, a plus a dagger, and y similarly is square root of h cross by twice m omega, b plus b dagger, we can easily rewrite this as k h cross by twice m omega times the matrix element of a plus a dagger and b plus b dagger between the states labeled by nx equal I and ny equals n minus I on the one hand, that's the bra on the left, and nx equal to j and ny equal to n minus j, that's a ket. Now, in order to figure out this matrix element, it's perhaps best to split up the work a bit. So we first look at the operator a plus a dagger acting on the ket I, n minus I. Of course, there's a corresponding bra which is sitting here, but what we will do is we will take the overlap of the corresponding bra with the second ket, which is b plus b dagger acting on j, n minus j. Now, using the fact that a plus a dagger has raising and lowering operators which only act on the first oscillator, the x oscillator, and hence only change the I label here, you get these two terms. The first one comes because when a acts on I, it changes I to I minus 1 with the square root of I in front, standard harmonic oscillator stuff. And the second term comes from a dagger acting on I to give you root over I plus 1, the prefactor times the ket I plus 1. Of course, the ny value is not affected by either the action of a or the action of a dagger. So it stays n minus I on both terms. Similarly, to figure out b plus b dagger acting on the ket j n minus j, it's rather simple. All that happens is only the ny index will change. It can either be lowered to n minus j minus 1 with a prefactor of square root of n minus j by the action of b. And the second term, of course, is what happens when it gets raised to n minus j plus 1 because of the action of b dagger. So, apart from the factor k h cross by twice m omega, calculating this matrix element here essentially involves finding out the overlap of the corresponding bra to this one with this ket, that is, finding the inner product between this ket and this one. And it's very easy to see, because of orthogonality of the states, you can only get a non-zero inner product from this term and this term if I minus 1 equals j, that is, if I is j plus 1. That actually ensures that both these two are the same state, so are these two labels the same, and that is why you get a factor of 1 from that. And the other possibility is when I plus 1 equals j, that also ensures that not only do the nx's match, the ny's also match, and you are going to get a non-zero overlap. Calculating that, I simply get our matrix element IVJ. I have just shortened phi n comma I to I here and phi n comma j to j here, I think that should lead to no confusion. What you get is kh cross by twice m omega, the factor in front, into square root of I times n minus I plus 1, basically square root of I times square root of n minus j, but j now remember has to be I minus 1 for this to really give you a non-zero value, and delta, you could either say I minus 1 comma j or I comma j plus 1, the same thing. And the other overlap which you get from these two terms is square root of I plus 1 into n minus I, delta I comma j minus 1. You can easily figure out that this is exactly what you are going to get. You should also be able to easily figure out that the other two terms that you could have got, the cross term this and this, and the cross term between this and this, will actually always be 0. So you will not get any contribution from those two terms. The form that the matrix takes should be obvious from this expression. The elements are 0 unless I is either equal to j plus 1 or j minus 1. And what that means is that all elements of the matrix are 0 except those which are in the diagonal just below the main diagonal or the one just above the main diagonal. And the elements themselves are also pretty easy to figure out. Apart from this kh cross by twice m omega, the elements are square root of I into n plus 1 minus I. And it takes a bit more effort to figure out that both these elements really are equal, at least at corresponding positions, so that the matrix turns out to be symmetric, as it really obviously should be, being the matrix for a Hermitian operator. And the only thing that you have to remember to figure out the exact form of the matrix is that I starts at 0. So, for example, the term here, the one in the second row, is actually the one corresponding to I equal to 1. So, square root of I into n plus 1 minus I simply becomes square root of 1 into n. The next term becomes square root of 2 into n minus 1, then 3 into n minus 2, and you go all the way down, where actually you get square root of n times 1 back again. So, basically, these factors keep on changing and then come back again to the original value. And it's pretty easy to figure out that the other diagonal, the leading subdiagonal, is actually exactly a repeat of this diagonal. So you get a symmetric matrix with an overall factor of kh cross by twice m omega. So this is exactly the matrix that we will have to diagonalize to find out the first order energy corrections because of the perturbation. And not only that, the eigenvectors corresponding to this matrix will actually give us the 0th order, that is the unperturbed energy eigenfunctions that we need to start from. Notice this is a special feature of degenerate perturbation theory. The perturbation actually dictates which of the particular degenerate combinations of unperturbed energy eigenvectors should you really start from to go on to the next level. Now, going by the standard rule in this class that I get to do the easy problems, whereas you get to do the hard problems, I will solve the simplest case explicitly. This is the case for the first excited level, that is n equals 1. This is only two-fold degenerate, so instead of this huge imposing looking matrix to diagonalize, I have only a 2 by 2 matrix to diagonalize. And the only non-zero terms are the two off-diagonal terms here, and they are going to be square root of 1 times 1, namely 1 each. So the matrix that I need to diagonalize is simply this kh cross by twice m omega times 0, 1, 1, 0. Remember, we are doing the case n equals 1, and the degenerate energy levels that we have started with are simply the states 0, 1 and 1, 0. Two-fold degeneracy, 2 by 2 matrix. And not only that, this particular 2 by 2 matrix is a very familiar one. 0, 1, 1, 0 is nothing but the Pauli sigma matrix sigma 1, and we know its eigenvalues and eigenvectors by heart. Now the eigenvalues for the sigma matrix are simply plus and minus 1. So the eigenvalues for this matrix, which is what I'm going to need to calculate the energy shifts, are simply plus minus kh cross by twice m omega. So the first order energy correction due to the perturbation kxy on the n equal to 1 level are simply given by plus kh cross by twice m omega and minus kh cross by twice m omega. As we have stated before, the perturbation lifts the degeneracy, the two levels which had the same energy to begin with. Once the perturbation is switched on, they are no longer degenerate, their energies have shifted. And what are these shifted energy eigenvectors? To figure them out, all you need is to figure out the eigenvectors of this matrix, which again should be very familiar to all of you. The matrix sigma 1 or sigma x has these obvious eigenvectors, which you must have studied before in your study of spin. I just put in a factor of 1 by root 2 to normalize, and these just give you the coefficients that you must use to combine 0, 1 and 1, 0 together to get the two corresponding 0th order states, that is phi n, that is in this case phi 1, 0, phi 1, 1, phi 1, 2, or whatever way you use as labels. In fact, what I will use are the labels plus and minus. So, the two degenerate levels corresponding to I equal to 0, I equal to 1 now have split into two distinct energy levels, and I am using plus and minus these two symbols to label them, and so my energy corrections are given by this quantity. Remember, this is only the first order correction, plus minus kh cross by twice m omega, as I have said, and these correspond respectively to the 0th order energy eigenvectors, psi 0th order 1, because this is n equal to 1 level, two possible degenerate levels that you started with now split into two distinct levels, no longer degenerate, labeled by the symbols plus and minus. And because of the eigenvectors that you had figured out for the perturbation matrix, these combinations are simply 0, 1 into 1 by root 2 plus 1, 0 into 1 by root 2, and similarly 0, 1 into 1 by root 2 minus 1, 0 into 1 by root 2. So this is all that first order degenerate perturbation theory can tell us. Let me stress once again, first order degenerate perturbation theory not only gives you the first order energy corrections, it also shows exactly what 0th order energy eigengets to use to proceed to the next level. Let us now turn to the calculation of second order energy corrections. Because we have two unperturbed energy eigengets to start from, namely psi 01 plus and psi 01 minus, those are going to be the ones we use to calculate the second order energy corrections E12 plus and E12 minus. And the formula that we had derived earlier essentially says that you have to sum up over all states with a catch, there's a prime here. I'm going to return to that in a moment. The summand is going to be the modular square of the matrix element of the states, the unperturbed states, V, and these psi 1, 0 plus or psi 1, 0 minus, as the case may be. Take the modular square of this matrix element and divide by the energy difference epsilon 1 minus epsilon of this state, which is epsilon nx plus ny. The prime on this sum, let me remind you, is to ensure that all the levels that we sum up over are from the other eigenspaces, not from the degenerate eigenspace that we are considering at the moment. So this sum will run over all values of nx and ny except for nx equals 1, ny equals 0, and nx equal to 0, ny equals 1, because those are the degenerate levels. Of course, this is great because otherwise you would have had a 0 denominator here, which is prevented by the fact that this sum does not run over the degenerate eigenspace. Now, because our psi 1, 0 plus minus are simply 0, 1 plus and minus 1, 0 by root 2, what we will do is we will simply calculate the effect of the potential, the operator acting on the state 0, 1 first, and then I'm going to calculate its action on 1, 0, and then take the overlap with nx and y in order to do this calculation in as simple a manner as possible. Now, the potential operator V is simply kh cross by twice m omega times a plus a dagger into b plus b dagger, and this goes and acts on 0, 1. So b plus b dagger here acts first, although let me just remind you that A and B, these operators commute. So you could have just as well moved the A plus A dagger across the B plus B dagger and made it act first. And given the fact that you have a 0 label here for the X oscillator, A acting on that would have made it go to 0 or made it vanish. So maybe it would have been a better idea to move the A plus A dagger first to this side and then do the calculation. But I've just decided to do it in a straightforward manner anyway, without any such tricks. We apply B plus B dagger on 0, 1. Remember, this only acts on the second oscillator, the Y oscillator. And B acting on 1 lowers that back to 0 with a square root 1 as a prefactor. And B dagger raises it to 2 with a square root 2 as a prefactor. And then A plus A dagger goes and acts on that. Of course, A acting on the first factor will kill it. You don't have that. A dagger acting on the first factor will raise the 0 up back to 1 with the square root 1 factor again. And A dagger acting on 0, 2 will give you 1, 2. And of course, the root 2 prefactor is still there. A acting on the second factor will also kill it. So instead of 4 terms that you might have expected, you end up with only 2 terms. Of course, if you had played the trick that we had discussed earlier with A plus A dagger moving on this side, you'd get the same result. Now, you can calculate V acting on 1, 0 all over again, but given that V is symmetric in X and Y, it's pretty easy to see that what you are going to get here is simply what you would get by interchanging the Nx and Ny labels. So you get 0, 1 plus root 2, 2, 1. So this is the potential energy operator acting on 0, 1 and 1, 0. So the potential energy operator acting on psi 0, 1 plus minus, the 0th order energy eigengets here, is simply what you get when you add these two and divide by root 2. So you get 1, 0 plus minus 0, 1 by root 2, and 1, 2 plus minus 2, 1, the root 2 just cancels here. So this is the operator V acting on the unperturbed eigengets, the precise combinations that you must use. And now you want to take the Nx Ny overlap. Remember, the Nx Ny overlap is only needed for Nx Ny belonging to eigenspaces which are not degenerate to our starting point. So our Nx Ny will not have these terms, so you can just ignore them as far as the overlap is concerned. So the overlap is simply going to be kh cross by twice m omega, Nx Ny overlap with this, which is delta Nx, 1, delta Ny, 2, plus or minus delta Nx, 2, delta Ny, 1. That comes from this term. Of course, you would get contributions from these terms in the matrix elements. However, those corresponding matrix elements will not appear in our sum. So we have just ignored them for the time being. Now it's straightforward to calculate the second order energy correction to the first excited level, E1, that 1 is of course first excited level, 2 is second order, and for the two unperturbed states, plus and minus. So the two levels essentially shift quadratically by this amount. You square the matrix element and divide by the energy difference between the state that you are perturbing and the state whose contribution you are taking the matrix element with. And here you can easily see that Nx plus Ny is 3 for this, whereas Nx plus Ny was 1 for our unperturbed levels. So the energy difference is simply minus 2h cross omega. So you get two terms only contributing in your entire sum. That is, Nx equals 1, Ny equals 2 will contribute, and Nx equals 2, Ny equals 1 will contribute. All the other infinitely many terms are actually 0. So you will get k square h cross square by 4 m square omega square coming from squaring of this. 1 square, which comes from this matrix element, by minus 2h cross omega. That's one term. The other term is this one. It's actually plus minus 1 whole square. So that's an error here really. I should change that. But anyway, it doesn't matter because you're squaring it. So it's going to give you plus 1 anyway, divided by minus 2h cross omega. Combining these terms together, I get minus k square h cross by 4 m square omega cube. Let us now take stock of the situation. We have calculated the first order energy corrections for the two degenerate levels we have found out that the energy corrections make the level split, and up to the second order, this is what the split energy levels look like. So the two levels which had equal energy to begin with, both twice h cross omega, now becomes two distinct levels, and the two distinct levels are given by this. Up to the second order in corrections, twice h cross omega, this of course was the unperturbed energy level, plus or minus k h cross by twice m omega, that's the first order energy shift, and now you have a second order energy shift that we have just calculated, given by minus k square h cross by 4 m square omega cube. Of course, we can carry out this calculation further and further down the line and get more and more terms here. But given the fact that we already know the exact answer to this problem, we are in a position to compare the exact answer with what we have obtained and check whether our work is at all okay or not. So, the exact energy eigenvalues. Just to remind you, we had two oscillators with frequencies omega plus and omega minus really. Omega plus and omega minus, just to remind you, were given by omega into square root of 1 plus or minus k by m omega square. And because you had two oscillators which are decoupled from each other, the energies were simply the individual sums, h cross omega plus by 2 plus h cross omega minus by 2 for the ground state, that is h cross omega plus omega minus by 2. And the first excited state energies, well, you have two different first excited state energies now. They are no longer both first excited state really now. Because of the perturbation, the energies are no longer equal. So you have one which is slightly lower, that's the E1 minus, the other which is higher, that's the E1 plus. And basically, what you have is an E1 minus, the omega minus oscillator, the oscillator with the lower frequency has been excited. The omega plus oscillator is in its ground state. And so the energy has risen above the ground state energy, h cross omega plus omega minus by 2, by an extra h cross omega minus. Whereas in E1 plus is the omega plus oscillator, the higher frequency oscillator, which has been excited. The lower frequency oscillator is still at the ground state level. And that is why the extra energy here is h cross omega plus over the ground state energy. And these are of course exact expressions. The expressions that we had derived using perturbation theory, namely E1 plus minus here, should be perturbative expansions in powers of k being the perturbation essentially, of these exact expressions. E1 plus minus, which are given by h cross omega plus omega minus by 2, namely the ground state energy, plus h cross omega plus minus. Now, in order to see whether our perturbative calculation actually matches up with this, what we need to do is we first write these out explicitly, omega plus and omega minus both in terms of h cross omega. So you get half square root of 1 plus k by m omega square plus half of square root of 1 minus k by m omega square. These are the terms, omega plus omega minus by 2, plus this additional piece which is 1 plus minus k by m omega square. This is of course either omega plus or omega minus as the case may be. And now all I have to do is expand this out in powers of k using the binomial theorem. So these two terms, basically the ground state energy, gives you contributions from the 0th order term. The one really comes from 1/2 from here, 1/2 from here added together. The odd term, the first order term, vanishes because of a plus sign from this and a minus sign from this. The second order terms both are equal, they add up and then you of course average them. So basically you get just the second order piece from any one of them. Minus 1/8, that's half into minus half by 2 factorial, the binomial coefficient. Remember you are expanding 1 plus k by m omega square to the power half. So this is the corresponding binomial coefficient into k square by m omega square whole square. That's basically the ground state energy. The additional piece that you get, of course, differs depending on whether you have the plus sign here or the minus sign here. So you get 1 plus half the first order correction into plus minus k by m omega square. This is what causes the splitting. The second order term is actually the same for both, because although you have plus or minus k by m omega square in the argument, you are squaring it. So you get the same contribution from both. Now putting all of these together, you get h cross omega into 1 plus 1. That's the 0th order term. Twice h cross omega. That of course matches our perturbative calculation. Then we get the first order correction from here, and you get h cross omega times k by m omega square into half with a plus or minus sign. So kh cross 2m omega with a plus or minus sign, as the case may be. And this exactly matches our first order perturbation calculation. And what about the second order term? Well, you get minus 1/8 from here, another minus 1/8 from here. So you get minus 1/4. And if you take the factors properly, you can simply see that you get k square h cross m square omega to the 4 in the denominator, but there's an omega in the numerator, so you get m square omega cube. And this is exactly our second order energy correction. So for this particular very simple problem, we have calculated the energy corrections up to order 2, and we have got exactly the same result as the exact solution. This of course should give us confidence that our method is actually working well and that we have understood how to apply it properly. We will go on to use it for more non-trivial problems in the next lecture. Until then, bye.